Okay, welcome to note set number 8, where we'll be talking about a little more about the transfer function and how we get it from the difference equations, and in particular how we end up with that transfer function being a rational function of z, so rational z transforms. So we're going through stuff from section 3.3 of Proacus and Monolacus. So in that section, they start with just some signal x of n, and they look at its z transform, and they talk about how it ends up being a rational function. And what I'm going to do is not follow their example. Instead, we're going to talk about the transfer function h of z. That's where we usually see the definitely have rational structure for most systems of interest. Not all, but most. So what we're going to do is look to see how we end up with the transfer function being a rational function of z. And by rational function, we just mean a ratio. You can see that word right there, ratio of two polynomials in z, and then we'll see what impact that structure has on system behavior, and how I didn't really proofread these too well apparently, how we can use all that insight to better understand the behavior of a system. So let's start with a difference equation here and see how we end up with the transfer function. And it's basically, we have to do this once, and then once we do it, we'll see the structure, and we never have to go through these steps again. So starting from the difference equation, we can take the z transform of the equation. So taking the z transform of the left side, z transform of the right side, maintains equality. And then we're going to use a combination of linearity, even though I don't say it here. We're going to pass the z transform through to each term, and then through pull the coefficients out in front of the z transform, so that we'll end up with the z transform of y of n minus 1, y of n minus n, and so on. And that's where we'll apply the delay property. So then each one of these terms, let's see, let me get rid of some of this stuff here. Just a second, bear with me here. Okay, then, so for example, once I take the z transform of this and apply the delay property, I'll get z to the z minus 1, z to the minus 1 times y of z. Then the next term I'll get z to the minus 2 y of z, all the way down to z to the minus n times y of z. And out in front, just y of z. So every one of these terms will have a y of z in it, and I can pull that out in front. Same thing here, I'll end up with an x of z that I can pull out in front. So I end up with a polynomial in z inverse, and another polynomial in z inverse. And notice that one of those polynomials has the coefficients of the output side of the difference equation, and the other one has the coefficients of the input side. And so now, interpreting this, I know that y of z, the output, must be equal to the input z transform times something, and that something will be h of z. We've already established that the output z transform must be the transfer function times x of z. So if I can just find out what sits in front of x of z, that will be the transfer function. So there it is. And we can see that immediately that it's very easy to write this down by inspection. So we don't have to do these steps every time. We just simply look at the structure. We have 1, A1, A2, A3, all the way out to AN, and those are the coefficients that go in front of the z inverses and so forth in the denominator. Then we have B0, B1, Bm, and those will go as the coefficients in the numerator. And we normally start with a difference equation that has y of n isolated without any coefficient out in front, but you could have an a0. But if you do have an a0 there that's not equal to 1, you can always normalize the equation without changing anything. You can do the same thing to each side of this equation and nothing bad happens. So if I have an a0 out in front and I divide both sides by a0, I will have normalized the equation. So I'll end up with an a0 over a0, or a 1 out in front. I'll have an a1 over a0, which I can rename as an a1 prime, say, and so on. So I can always normalize it so that I have a 1 on that term for y of n, and likewise a 1 for the z to the 0 term in the denominator. So that's usually the standard form that we use. So the key is that given a difference equation, you should be able to, just by inspection, immediately write out h of z, and vice versa. If we have h of z, we can manipulate it into the z inverse form. It's important to get it into the z inverse form, and you can do that just through some algebra, multiplying top and bottom by some z to the minus whatever to clear out all the positive powers of z and be left with just negative powers of z and possibly some z to the zeros out in front. Then you can immediately write down by inspection what the difference equation is. Okay, so once we have the transfer function, we have it in the z inverse form. It's very easy to convert it into the z form. So if we, how we do that will depend upon the relationship between m and n. But regardless what the relationship is, if you end up, multiplying all this stuff out, you'll end up with something out in front that is just z to the n minus m. And we'll see in a minute whether that n minus m is a positive integer or a negative integer, or 0, depending on the relationship between the integers n and m. But nonetheless, we end up with a true polynomial in z in the numerator and another true polynomial of z in the denominator, and we'll just call those b of z and a of z because of the symbols that we've used for the coefficients. And to proceed further, we should really make an assumption that there's no common root in these two polynomials, and if there is, we'll assume that they've been canceled out. So if we factored out the numerator and factored out the denominator, looked for any common factor in them, we'll assume that we've factored out and canceled that one term. So once we have that, then we can define poles and zeros of the transfer function. So the poles of the transfer function are the values of z that cause the transfer function magnitude to go to infinity, and the zeros are the values of z on the complex z-plane that cause the transfer function to go to 0. So our whole purpose in getting it into this form, or equivalently this form above it, our whole purpose in doing that is so that we can very easily find the poles and zeros. You can find them from that form, but if you get it into the z form rather than the z inverse form, it's much, much easier and reliable to find poles and zeros. So once we get it into the z form, we look at the a of z polynomial on the bottom, and we find its roots, and that tells us the poles. So we're going to have n poles that come from the denominator, and then we look at the roots of the numerator polynomial, and there will be m zeros, because by definition the values of z that are roots of that cause the denominator to go to 0. Likewise, the roots of the I'm sorry, the numerator to go to 0. The roots of the denominator cause the denominator to go to 0, which causes h of z itself to go to infinity. So this is all good. And then we have this term out in front, the z to the n minus m. And what it contributes to the poles and zeros depends on the relationship between n and m. So if n is greater than m, we end up with z to a positive power here, and we can interpret that as being grouped with the numerator, in which case it will give us some n minus m zeros. Likewise, let me try to get rid of this stuff here. Likewise, if n is less than m, then this ends up z to some negative power, which we can then bring down with the denominator as a positive power in the denominator, and that will add an additional m minus n poles at the origin. And you can see why they should be at the origin, because this is just z raised to some power. Okay, so those z terms out in front, the z to the n minus m gives us either poles or zeros at the origin. Everything else will give us poles and zeros not at the origin. And if we figure out where all these poles and zeros are, and we plot them on the z-plane, we call that a pole zero plot. And we'll use x's to represent the locations of the poles, and we'll use circles, little circles, to represent where the zeros are. So here's an example. We start with this difference equation. We, by inspection, say here's our numerator. We're going to have 2 times z to the 0 and 1 times z to the minus 1. So there's that numerator. Then we're going to have a 1. And then we're going to have a minus 1 over square root of 2 times z to the minus 1. And then we're going to have a 1/4 times z to the minus 2. And that gives us our denominator. So then we take that and we look at it and we say, well, our most negative exponent is -2. So if we multiply top and bottom by z squared, we haven't changed anything because we're doing the same to the top as we are to the bottom. When we multiply the z squared through on the denominator, we're going to end up with a z squared, a z term, and a z to the 0. And so that's what we get there. Up in the numerator, we're going to end up with a z squared plus z. So 2z squared plus z. And then we can factor out the 1z out in front so that we end up getting something that goes all the way down to a constant. And so if we look at that, let me clear that away here. If we look carefully at that, we can see that in the numerator, we've got a z term out in front that has a positive 1. So that means that our n is greater than our m, and we saw that that was true. So we're going to end up with a 0 at the origin. And we're going to end up with a 0 at z equal to -1/2. So if I put in -1/2 there, that parentheses term goes to 0. Then in the denominator, we've got a polynomial that we have to factor. And if you factor that, you see that you end up with conjugate roots. And since the coefficients of the denominator polynomial, well, all these polynomials must be, at least as we're restricting them here, to be real valued, we know that the roots of these polynomials must be complex conjugate pairs if they're complex. So we see that we get the 1 plus j and the 1 minus j. So if we plot those on a z-plane, either by hand, using x's to mark poles and circles to mark zeros, then we can create a pole zero plot. You can also use the command z-plane in MATLAB. So you put in the coefficients of the polynomial. And here you can go directly from the z inverse form. So you can put in the 2 and the 1, and then the 1 and the minus 1 over square root of 2 and the 1/4. So in that case, you would go directly from this form. You don't have to go to the z form. We go to the z form to do it by hand. So to use the z-plane, you should go directly from the z-inverse form. And then it makes a nice plot, and you can see, a little hard to see the origins. We have 1, 0 at the origin. We have another 0 that's over here. That's the negative half. And then we see our 2 complex conjugate poles there. So a very simple way to go from the difference equation, and in fact you can directly go from the difference equation to the z-plane command if you want. And so very easy to do that and get a nice plot of the pole 0 diagram. So linking these poles of the transfer function to the region of convergence is an insightful thing to do. So we've seen that the transfer function goes to infinity at a pole. So obviously the poles cannot be in the region of convergence. Because by definition, since the poles mean h of z goes to infinity, that is what we mean by not converging. So the region of convergence must be devoid of poles, and so there will be no poles in the region of convergence. And in fact, we can go even farther and say that once we know where the poles are, we know that the poles will be right on the edge of the region of convergence. If they weren't, then we could just make the region of convergence just a little bit bigger without hitting a z point where the transfer function explodes, and so that would be allowable. So the region of convergence has to go right up to and just just touch where the poles are. So in that sense, we can see that the region of convergence is an open set, not a closed set, at least where on the edges where the poles are. So this is our link between the region of convergence and ideas of where poles are. So let's just take a look at an example to illustrate that. Just pointing out that on our previous example we had a 2 there, which I've removed. So we've already found the poles and the zeros for this system, or at least one that's very, very similar to it. So instead of having a z equal to negative 1/2, we now have z equal to minus 1 because of the lack of the 2 there. But the poles are going to be the same. And we can verify that this is a causal system if we put in a delta function with 0 initial conditions and we just recursively solve for y of n. We can see that we won't get any output until delta of n actually occurs or goes to non-zero. So we can see that it's causal. So we know that our impulse response is a causal function. And therefore we know that the region of convergence will be outside a circle of some radius, so we just have to find out what that radius is. And since we know that that circle, which will be the edge of the region of convergence, has to be right at the poles, all we have to do is find where the poles are, which we've found, and they are in rectangular form. If we just find what their magnitude is, that will give us the radius. So we find their distance from the origin or their magnitude. So we're just taking the magnitude of that complex number. We pass the magnitude in through that positive real number out in front, 1 over 2 square root of 2. So we now have magnitude of 1 plus or minus j, apply the formula for computing the magnitude of that, and we find out that the radius of our region of convergence circle is 1/2. So this would be a radius of 1/2, and it goes out, and those poles are right on that circle of radius 1/2, and the region of convergence is everything outside of that circle of radius 1/2, not including the actual point or the actual circle of radius 1/2. And then note that we have a 0 outside that circle, so zeros can actually occur either inside the region of convergence or not in the region of convergence. It doesn't really matter. But poles cannot be in the region of convergence. So in this case, we see that we had a causal system. So our h of n is causal. And if you look at this, if you actually solve this thing, you'll see that it is infinite in duration. So this is consistent with our results earlier, saying that for a causal infinite duration signal, h of n in this case, the region of convergence will be outside of some circle of an appropriate radius. So that should tie together a lot of the ideas that we've been seeing. So we've got the transfer function, which we can get from the difference equation. We've talked about the pole zero diagram to some extent. Not everything about it yet, but we're starting to see some of the things that we can see from the pole zero diagram. And so now we want to link the transfer function to the frequency response. So remember I was saying in a couple of notes I had previously, I was saying that we use the transfer function and z-transform ideas for a lot of design and analysis of how a system's going to behave. And then when we do finally want to think about, well, what is this really going to do to a signal, we switch back to frequency response, assuming that the system is stable. So if the system is stable, then we can use the DTFT in the frequency response. And we know that since the DTFT is the z-transform evaluated on the unit circle, we can do that only if the unit circle is inside the region of convergence. So for causal systems, the unit circle is inside the region of convergence if all poles are inside the unit circle. So we can deduce that from our previous insight on the previous slide or two. So if all the poles are inside the unit circle, and you may remember that that was our condition for stability, so we could also say if the system is stable, then we can get the frequency response from the transfer function just by replacing z with e to the j, and here I'm using capital omega. The textbook uses little omega. Yes, I admit I borrowed notes from my signals and systems class and didn't completely edit them to change them. Well, all right. So anyway, so we can do this very easily using a MATLAB command and then be able to plot what this thing looks like. And this is a really nice thing to be able to do. So we start with our transfer function written in the z inverse form. It's important to be in the z inverse form here. And then we go create in MATLAB a vector whose coefficients are the coefficients of that z inverse polynomial, starting from the term with z to the 0. So we then we write b0, b1 all the way down to bm in a vector. We do the same thing with the denominator polynomial, and here I'm showing that we could have an a0 that's not normalized to 1. Then we have to create, and this is just one way to use this command freq_z, but I actually like it best this way, and I think this is the most useful way to use it. But there are some other ways to use it, and if you type help freq_z, it'll spew out several different ways to use this. And that's the problem with the help in MATLAB is that MATLAB is such a flexible structure for many of its commands that the help can often seem fairly intimidating. So my preferred way of using this is to create your own omega vectors. So these are the frequency points, the discrete time frequency points at which you want to evaluate the frequency response. So we know it has to go from minus pi to pi. What we don't know is how close our spacing should be. So this syntax here that I'll explain in a little more detail, since you haven't necessarily had MATLAB training before. So this is just a cursor in MATLAB, and this is just a way to enter those coefficients into a vector, and then this syntax here. Let's see if I can get a little thing going here. We've got the problem with this is like when I do this, I can't see where I'm pointing. I'll just assume that I have a pointer going on under there. Okay, so the minus pi colon then some number colon pi. So this is telling MATLAB to create a vector starting at minus pi, ending at pi, with whatever spacing I put in between. So you might put a spacing in that's like, 0.001 or 0.00001 or something like that. So the smaller you make that number, the larger the number of points you'll get in your omega vector. But the finer the grid will be on which you're plotting your frequency response. So typically I just kind of play around with it. 0.001 is kind of my go-to value. And then when I plot it, if my plot looks kind of jagged, I'll make it a little bit smaller and see if that smooths it out. I also want to point out that at the end of each one of these commands, so let me switch back to this and get rid of these things. So at the end of each one of these command lines, you'll want to put a semicolon there. That will suppress it spewing out the computed numbers. For the first two, it won't necessarily be that bad, but for the omega command, especially if you make it 0.001, it'll spew out onto your screen, 1,000 some points, 6,000 points, I guess, something like that. So, put the semicolon there, and it will keep that from happening. Then you just run this command, h is equal to freq z, with the NUM and little typo here, should be just DEN, and then put omega there, and put a semicolon at the end, and it will compute the values of h, not the z transform, but the DTFT, so at different values of omega. And then you can plot the absolute value of it to look at the magnitude, and you can plot the angle of it to look at the phase. And this is a little trick I do all the time. I plot it versus omega divided by pi. What that does is MATLAB will put a nice little grid mark at 1 when you plot, and you interpret 1 as pi, and -1 will be negative pi. And chances are it'll put nice tick marks at like 0.25 and 0.5 and things like that. So 0.5 would be pi over 2. So these are landmarks that we usually are interested in. And if you just plot it versus omega, you won't really see those nice mile markers, so to speak, because MATLAB doesn't like to put mile markers or tick marks at like 3.14159, right? So this is just a little trick. Then you have to, I don't show any of the labeling. There are commands for X label and Y label, and we'll illustrate those in some additional material. I don't put any labels on the plots, but I will warn you that if you make a plot and you put no labels on it, it's not a plot. It's just art. So we're not doing art in this class. We're doing science and math and engineering. Well, math and engineering anyway. And so we want plots, not art. So make sure you label your axes. Otherwise, it's just art. Not that there's anything wrong with art, but it just doesn't belong in our engineering results. Okay, so that makes a really easy way to plot your frequency response. So look at what we're setting up here. We can go from difference equation to transfer function to a plot of the pole zero diagram to a plot of the frequency response. All these are things that we can use as tools to visualize what a given system looks like. So if I give you a system, you can kind of see what it's going to look like and how it's going to behave. But once you start being able to do that, then that enters into the design process. When you're trying to design a system to achieve a certain goal, having this insight as to what a given system looks like will help you figure out how to do the design. Okay. So here's an example of visualizing this kind of thing. Suppose we start with an h of z that looks like this. And since we have a 0 in the denominator at z equal to 0, we've got this 0 at the origin over there. Let me get rid of that before we go too much farther here. So we've got, and then in the denominator here we've got two complex conjugate roots, and I've written the poles in polar form. No pun intended there, because that's how we like to think about poles and zero locations for discrete time. The magnitude and the angle of these things will be of most importance to us, and you'll kind of see why in just a minute. So we have poles that are at 0.8 magnitude out from the origin and at an angle of plus or minus 0.3 pi. So one is up there and the other one is down there. So that defines where our two poles are. So we've got that pole zero diagram, and then we can imagine plotting the magnitude of this transfer function over the z-plane. And we have to imagine that the poles are going to be pulling this surface up to infinity, and we can see those two things going up to infinity at the appropriate places. And then the 0 is going to be tacking this down, so it's kind of back behind this pole. You can't quite see it. But right at the origin, it's tacking the surface down. And then everywhere else, the surface is just kind of hanging like a tent surface. With one additional extra thing. You'll see that it never actually touches, never goes down to 0, except where there's a 0 tacking it down. So it's like we're pitching a tent with infinitely tall tent poles, with stakes staking it down to the ground, but the ground is actually like an air hockey table. So unless we tack it down with a stake, or a 0, as we really call them, the tent surface is going to kind of float above the ground, or the air hockey table. So that's how we visualize this. And then finally, we know that to get the frequency response, we need to evaluate this on the unit circle. So here I am again using my capital omega instead of little omega. But hopefully by the end of this course, you'll be very comfortable flipping back and forth between lots of different symbology, which is a good technique to get used to, because when you're actually doing work rather than doing a course, you're drawing from a lot of different resources, and everybody uses slightly different notation, as you might be seeing already. Excuse me. So if we evaluate on the unit circle to get the frequency response, that would be this dark line that this dark curve that I'm showing here. That is those are the values of the magnitude of the transfer function evaluated on the frequency, evaluated on the unit circle. So looking at that, that curve tells us what the frequency response is going to look like. But wait, we're used to seeing the frequency response splayed out on a linear axis, not circled around on itself on this plane. So to see that, go to the next slide. So here I've extracted that curve. I basically think about I've cut away all the other parts of the Z transform, transfer function, magnitude, and left just that curve. And what I'm going to do is cut right here at the Z equal to -1 point. And what angle is that? Well, it's angle plus pi. It's also angle minus pi. So I'm cutting at the plus and minus pi point, and I'm going to unfold this just like I've taken a Burger King crown that I just got at Burger King, and they've already assembled it for me, and I'm going to take it apart and lay it flat. So when I take this, I cut here, I open it up, and it becomes this. And so now notice that I am plotting here versus omega divided by pi. So -1 is negative pi, and +1 is plus pi. So this little spike here is this spike here, and the spike over here is this spike here. Scooting down is this scooting down on the other side is this scooting down in the middle is this thing here. So let me get rid of a whole bunch of that stuff before we go on here. So hopefully you can visualize going from the transfer function surface plot to cutting away everything, taking the Burger King crown, cutting in the back, unfolding, and laying it out on a linear axis. And so this is the frequency response, the magnitude of the frequency response, plotted versus the omega axis. And so that's how we visualize this. And so we can now see the effects of the pole placement. And remember, these poles were at a radius of 0.8 from the origin. That's why these are fairly pronounced peaks. If we moved the poles farther away from the unit circle, so say we had it not at 0.8 magnitude, but maybe 0.3, now those poles have much less influence on what the surface is doing on the unit circle, and so we would see less of a pronounced peak. Also notice that the angle of where these peaks occur is very, very close to pi over 3, and that was the angle of where the poles were. So by moving the poles to different angles, we can put peaks at different frequencies. So the angle of where the pole is corresponds to a frequency. And we can see that. That comes from this view. When we cut and unfold, the minus pi angle becomes the minus pi point on our linear axis. And so now we see why, first of all, we talk about discrete time frequencies in terms of radians per sample. We also can see the periodic nature of the DTFT. So we've only shown from minus pi to pi on this plot over here, but if we extended that and plotted a DTFT showing outside of that, we would see that it's periodic to pi. And that's just because we're going around the unit circle around and around and around. So it doesn't matter how many times I go around, I'm right back onto the same plot. This explains a lot of the characteristics that we've seen in other ways. So here's a nice little example that comes out of a book by B.P. Lathy called Signal Processing in Linear Systems. And basically he's showing a bunch of different pole zero diagrams and what the magnitude of the frequency response looks like. And he's only showing from 0 to pi. You can exploit the symmetry on the minus pi to 0 part. So the magnitude has even symmetry. The phase plots have odd symmetry. So we start off up at the top here. We've got a single pole, and it's on the real z-axis. So that's going to cause the frequency response to be pushed up around an angle of 0. And remember, angle of 0 is frequency of 0. So we get a little push up at frequencies near 0. And then as we go to frequencies around here, closer to pi, remember the tendency of the surface is to fall down, but it won't hit unless we actually tack it down, because we're, remember, on an air hockey table. Okay, so that's why we don't see it going down to 0 there. So what happens if we put a 0 at the origin here? We can actually show that putting a pole or 0 at the origin does nothing to change the magnitude. And you should be able to convince yourself of that. Take an h of z, multiply it by a z, so now you have z times h of z. That's your new system. It has a 0 at the origin because of the z out in front. Replace z by e to the j omega to get your frequency response. Now take the magnitude of that and convince yourself that that z out in front, once it turns into an e to the j omega and you take the magnitude, just vanishes, goes to 1. So it doesn't change the magnitude. It does change the phase response, though. So by putting poles and zeros at the origin, we can leave the magnitude response the same, but change our phase response. Continuing down here, we've kept our pole near DC, near 0 hertz, or 0 radians per sample, rather. So we still have a low pass nature, but now we've put a 0 right at plus and minus pi. And so what we see now is that, unlike here, where the surface could not go down and touch the air hockey table, we are now tacking it down to the air hockey table. So it will go down exactly to 0. So we've, in some sense, made this a better low-pass filter because we are now forcing this down a little bit farther. And if we take that idea to an extreme, we throw in a few extra poles here to try to push things up and hold the passband up a little bit better. And then we put a multitude of zeros all at the origin. And it's kind of hard to see how many there are there, but I'm counting 3. So if we tack 3 zeros there, then we see that we get an even smoother approach to going down to 0 at the place where the zeros are. So by using multiple poles to push things up and multiple zeros to pull things down, we can better craft the shape of our frequency response. Now, just in case you're thinking, oh my goodness, I'm going to have to play around with this and figure out, put a pole here, put a pole there, put a 0 there, put a 0 there, and what do I get? Well, yeah, it's kind of fun to play around with that, and some simple designs can be done that way. But we'll see later on that there are some very nice tools for doing design that doesn't really require us to think like this, but just using those tools blindly without really knowing these insights is very, very dangerous. So I would encourage you to not take that attitude. We can flip things around, put our poles over here and put our zeros over here. Now we've got zeros at angle of 0, so at the frequencies near 0, we're now tacking things down. And we've got poles over here near angles of plus and minus pi, so we're now pushing things up at pi. And so this structure gave us a low-pass filter, this structure gives us a high-pass filter. So by figuring out where to put our poles and zeros, we can make all sorts of different filters. And we'll explore this much more throughout the rest of the course. So the rest of these notes here, I want to just hit on a few additional things, like, for example, the Cascade of Systems. We mentioned that briefly when we talked about convolution. But suppose we have one system that has frequency response, transfer function H1, and we run its output into a second system, H2, so it has its frequency response and transfer function. So if we look at here, we can immediately see that the output will be X times H1, regardless of whether we do it as DTFT or ZT. Then we take that and we apply Y of omega multiplied to H2. So Y gets applied to H2, but if we plug in H1X for Y, we end up getting something that looks like this. So X gets affected by a system, an effective system, that is the product of H1 times H2. So if we have two cascaded systems, the total frequency response or transfer function is just the product of the two individual systems' results. And we can generalize that to a cascade of n systems very simply. So that's the idea of cascading systems, and sometimes we want to take a cascade of systems and replace it by a single system, or sometimes we want to take a single system and break it into a cascade of multiple simpler systems. So either way, knowing this result helps us those. I want to tie all this back to impulse response, which we've talked about already when we talked about convolution. Now, most of our system insight does come from transfer functions and frequency responses, but sometimes looking at the impulse response really gives us a nice insight. So if we wanted to find the impulse response of a system, so suppose you have some system sitting there in the lab and you want to know what does the impulse response look like. All you got to do is run a sequence of zeros, then a single one, and then more zeros in as your input, set the initial conditions to 0, and look at what comes out. And so if the system is causal, since this starts at n equal to 0, you better not have anything starting prior to n equal to 0. Now, to link all of this to the transfer function, so we know that we can find the output of a system in the z domain by taking h of z times the z transform of the input. So the z transform of the delta function we know is equal to 1. So this just becomes the z transform of h of z. So h of n is the z transform of h of z. So in other words, h of z and h of n form a z transform pair. Likewise, h of n and h of omega form a DTFT transform pair. And so that's a very nice result, and that was something on our big system diagram, the diagram that shows all the system relationships. And then finally, if we think about our system transfer function that looks like this, if we make a few simplifying assumptions to just kind of get an easy scenario to think about, and we do an inverse transform of this, something in this form, maybe not exactly in that form because of these assumptions, but pretty close, we can find that we get a sum of a bunch of exponential terms, and each one of those p sub i's is one of the poles. And so if we want our impulse response to decay, which we do, remember it has to decay fast enough for it to be absolutely summable, for it to be stable. So for stability, we want all of these individual terms that I've circled to go to 0, to decay down to 0. So that means that those numbers, P1, P2, and so forth, need to have magnitudes that are less than 1. So that's just yet another way to see that poles inside the unit circle lead to a stable system. So just another way of visualizing that. So once we have this idea, we can kind of categorize what kinds of impulse responses we get from different pole and zero positions. And mostly it's the poles that we're interested in. So if we have a simple system that looks like this, and I'm pointing out that the book doesn't actually show the zero on the z-plane here, which has kind of annoyed me. So I put the zeros in. And we can look at scenarios here where this A value takes on different values on the z-plane. So if A is between 0 and 1, we'll have a pole on the real axis that's inside the unit circle, and this thing will decay. So that ends up having a structure that is A to the n. In fact, all of these, if you look at our z transform table, all of these h of n's will have the structure an times u of n. So when a is between 0 and 1, we see that that thing is going to decay. When a is equal to 1, we get a pole right on the unit circle. It never decays. Hey, unstable system. Pole on the unit circle. Impulse response that never decays. When a is greater than 1, we see the pole is now definitely outside the unit circle. This thing is going to explode. Again, not absolutely summable, so not stable, but we knew that. A pole outside the unit circle is unstable. Now let's look at negative A's. So same kind of thing. If A is negative but still in magnitude between 0 and 1, it's still going to decay, but now it's going to oscillate. So the distinction between here and here is decaying, but one doesn't oscillate, the other one does. Then we have A equal to minus 1. So similar to the A equal to 1 case, never decays, but now it just oscillates back and forth between basically plus 1 and minus 1. If A is less than negative 1, now this thing's going to oscillate but explode. So by just looking at these pole positions, we can kind of get an idea of what the impulse response is going to look like for a very simple first order system. Now, if we had a repeated pole, we get some interesting behavior here. When the pole is inside the unit circle, and you can see that they've illustrated or they've demarked it with a m equal to 2. That's the multiplicity. Sometimes you'll see just the number 2 next to it. So what we see happening here is we have, instead of decaying down, it actually starts to ramp up, but eventually decays down exponentially. And you can solve, I would encourage you to try to find what h of n is for these. It may take a little bit of reviewing how to do partial fraction expansion for the case of repeated roots and so forth, but it could be interesting for you to do that. If we have repeated roots right on the unit circle, this thing's going to just keep going up linearly. Repeated roots outside the unit circle, it's going to go up exponentially. And then over here, all the same kinds of things except now oscillating. So lots and lots of insight can be gained just by having a good feeling for what a pole in one place is going to do to both the frequency response as well as the impulse response. And then we get a second order system with some complex roots, and we can see that when we have poles inside the unit circle, it's going to decay. On the unit circle, never really decays, at least in overall height. And then outside the unit circle, it's going to explode. And then the last thing that I want to point out here is the angle. The angle is how rapidly this thing oscillates. So we can now see, let's just focus on the point where, the case where the pole is inside the unit circle. The radius is going to control how fast it decays. Closer to the unit circle, the slower it decays. Closer to the origin, the faster it decays. And the angle that it will be, that where the pole is, sets how fast the thing oscillates. So if the angle is close to the real axis, then it will oscillate very, very slowly. If the angle is more out this way, close to plus or minus pi, then the oscillation will be very, very fast. So I encourage you to think about these relationships. The better you can nail them down and internalize them, the better off you'll be able to do a lot of the other things that we'll need to do in this area of study. All right, we'll see you in the next set of slides.